In this question, we're going to predict if a precipitate forms or not based on this scenario. So we have 15 mils of a 0.024 molar lead nitrate solution is mixed with 30 mils of a 0.030 mole per liter potassium chromate solution. Will a precipitate form? So your first step, if it's not already done for you, is to do a double displacement reaction and to predict if you're going to have a precipitate or not in that equation. But that doesn't necessarily mean a precipitate will form. We have to do a test with QSP versus KSP to figure out if that will actually precipitate out of the solution, given the concentrations you're provided in the question. So here's our double displacement reaction. We have our lead nitrate reacting with our potassium chromate, and we're going to have our equilibrium like this over here, and that's going to produce some lead chromate and some potassium nitrate. And if you look at your solubility table, you'll see that this is a precipitate and this is the aqueous substance. So we care about that precipitate there. Now, our goal is to find the QSP of this precipitate and compare it to its QSP. So what I like to do is I like to write out a little equation for the dissociation of the precipitate, because it still does dissolve in small quantities, and the whole point is seeing if it will precipitate by going more to the left. So we're going to make a equilibrium for our precipitate. It's going to be PB plus 2, because we can see it was plus 2 on this side here since there was a 2 there. Aqueous, and chromate is minus 2, so CrO4 2 minus aqueous. And what we need to do is we need to actually figure out what the QSP is going to be and compare it to the KSP. So the QSP is essentially just making a KSP expression, but we don't know if we're at K. So to make a QSP expression, we do QSP is equal to the concentration of the lead times the concentration of the chromate. And we can go find the KSP by looking at our table. So the KSP is going to be for lead chromate is, let's go find it here. So under KSP, we have lead 2 chromate 2.3 times 10 to the power of negative 13. So 2.3 times 10 to the power of negative 13. That is our KSP. Let's just make a different color here so we can see, times 10 to the power of negative 13. So we somehow need to find the concentration of the lead and the chromate after the reaction has happened. And we need to see if we plug it in, will it give us a QSP that's larger than the KSP or not? And then from there we can determine if a precipitate will form. So we have to use the information from the compounds that we're reacting to determine the concentrations in the new solution. So let's go ahead and do that. We'll do one compound at a time. I'm going to leave some room because I'm going to come back up here to finish the problem at the very end. So we'll start off with the lead nitrate. Lead nitrate. If you were to make a dissociation equation for it, would look like this. And there's 2 of them. And so we're going to make an ice table to predict the concentration of lead that would be in this solution. Now, all of the lead nitrate must have been dissolved since there was no precipitate to begin with. It was all dissolved. So what we're going to do is we're going to write out the concentration of lead nitrate to begin with, which is 0.024. We had 0 of this to begin with because it wasn't dissolved just yet. Only when we put it in a solution did it dissolve. The change is minus x plus 2x. And then over here we should have 0. And over here we should have x and x. So this is essentially like using molar solubility to find the concentration of the ions that are present. So essentially what we found is that X must be equal to this molar solubility there, because that minus X gives you 0. So essentially X is the concentration of the Pb2+, which is equal to 0.024 moles per liter. Now, we don't really care about the nitrate because the nitrate is not in our main precipitate, which is the thing we're analyzing over here. We just care about the lead specifically from the lead nitrate. If nitrate was in our precipitate, then we would care about that. But right now we don't. And by the way, there should be 2x, not x there. So this would be the concentration before mixing. Keep in mind that we actually mixed two solutions together. So we can't use this as the concentration in our QSP. This QSP is actually happening in a new volume. Remember that the new volume, let's call it V2, it's a new volume, is going to be the combined volumes of the solutions you're mixing together. So 30 and 15. So that's 30 plus 15. That's 45 milliliters, or 0.045 liters. So we need to use our dilution formula to find the concentration of the lead in 45 liters, or 0.045 liters, instead of 15 milliliters. So we're going to do C1 V1 is equal to C2 V2. So C2 would be equal to C1 V1 over V2. And that's going to be equal to our 0.024 molar times the volume 1, which was 15 mils, so 0.015 liters, over our new volume, 0.045 liters. Cancel out the liters, and you're left with molarity. So we have 0.024 times 0.015 divided by 0.045, and we get 0.008 molar. So this is the concentration of the lead once we've mixed the two solutions together. And I'm going to go ahead and plug that in here right now, just so I can do the work at the same time. So it's going to be 0.008. And now I'm going to go and try to figure out the concentration of chromate using the other compound, the potassium chromate. So I'm going to do the same step, but for potassium chromate. So K2CrO4. Make your dissociation. We have 2K plus over here, aqueous, plus CrO4, 2 minus aqueous. We'll make our ice table. Our initial concentration was 0.030. We have minus x over here. This was 0 and 0. This is plus 2x. This is plus x. Here we have 2x and x. And here the whole thing is dissolved. So that means is that x must be equal to 0.030. We don't care about 2x because that's potassium ion, and the potassium is not in our precipitate. It's in the part that remained dissolved. So we really just care about our precipitates, or the chromate part. So we have that, therefore, x, which is equal to the concentration of chromate, is 0.030 molar. But remember, this is in the initial volume of this solution, 30 mils. So we have to use our C1V1, C2V2 to find it in 45 mils. So just from the previous example, C2 is equal to C1V1 over V2, which is going to be 0.030 molar times the volume 1 was 0.03 liters, because that was 30 mils, divided by the V2, which is 45 liters, 45 mils, so 0.045 liters. Cancel out the liters, and you're left with molarity. So we have 0.030 times 0.03 divided by 0.045, and we get 0.02 molar in that new solution. So we can plug that in here. We get 0.02 molar, and we'll get times 0.008, and we get 1.6 times 10 to the power of -4. So this is our QSP. And so now we can compare the QSP to the KSP, and we'll do that just up here. Normally there'd be more room. I like to save a bit of room between step 2 and 3, just so I can do everything in one area. Actually, I can probably fit it in here. So so we see that the QSP is larger than the KSP. So QSP is larger than KSP. So what that means is that the solution is super saturated and a precipitate forms. So what did we do in this example? We were told that you're mixing two solutions together, some lead nitrate and some potassium chromate. We made a balanced equation to illustrate that and predicted what the precipitate will be and which one would not be the precipitate. Just because you have precipitate in your equation does not mean one will form. You have to double check using the QSP versus KSP test, so the trial ion product. To do that, you take your precipitate, you make a dissociation equation for it, and you write a QSP expression for it, and you find the KSP in the table. So that way, when you're ready, you can calculate QSP and compare it to the KSP directly to come up with your conclusion. So to find the QSP, you need the concentrations of the different ions in this new solution. So you need to use the compounds from which the ions came from. So to find the lead concentration, we took lead nitrate, made a dissociation equation, an ice table, and we found the concentration at equilibrium to be this. However, this is in a new volume. The new volume is the two volumes added together. So we had to use our C1V1 is equal to C2V2 to find our concentration in the new volume. And we plugged that directly into our formula here. We did the same thing with the other compound to find the other ion in the precipitate, which was a chromate. We didn't really care about the potassium because that's not in our precipitate. If it was, we would care about that instead. So we found that to be the concentration in the solution before mixing. And then we had to find it after mixing using our dilution equation. And once we did, the 0.02 was plugged into our QSP, and we found the QSP value. We then compared it to the KSP and saw the QSP is larger than the KSP, which means that our solution is supersaturated in these concentrations, and therefore a precipitate will form. So this stuff here will come out of the solution, leaving very, 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 very little behind in the solution because it's such a low solubility. Remember, for KSP, the lower it is, the higher the lower the solubility, because you go towards you favor the left side more, which is your solid as opposed to the aqueous. So in this lesson, we saw an example of how to predict if a precipitate will form. You can try out the other examples provided here. They're essentially very similar, but they have different compounds and different concentrations.